Hello students, today I am delivering the lecture about the MOSFET scaling and small geometry effects. So basically the MOSFET is metal oxide semiconductor field effect transistors. So basically it is the high density chips in MOS VLSI technology that requires the packing density of MOSFET used in the circuits is as high as possible, and consequently that the size of the transistors are as small as possible. So the reduction of the size dimension of the MOSFET is commonly referred to as a scaling. So due to when we use the scaling, obviously operational characteristics of the MOS transistors will change according to the reduction of the size or its dimensions. So basically in type of size reduction, that are basically two types. First one is full scaling, that is also called the constant field scaling, and second one, that is the constant voltage scaling. So basically the both types of scaling approaches will be used for the reduction in the size of the MOS transistors. So scaling of the MOS transistors is concerned symmetrically reduction of the overall dimensions of the device allowed the available technology which is used in the technology process, and while prevailing geometry ratios found in the large devices. So the proportional scaling of the all devices of the circuits will certainly result in reduction of the total silicon area occupied by the circuit, so thereby increasing the overall function density of the chip. So describe the device scaling when we introduce the constant field factor, basically that is constant field factor, that is equal to S, is greater than 1. So according to the history of the reduction in size in typical CMOS gate structures or gate arrays, basically for new generation of the manufacturing technologies replaces the previous ones, and about the decades and 2 or 3 years before, the scaling factor scaled down by the factor of S according to minimum feature size of the one generation of the next device. So we have present a table by which I have introduced here the different type of scaling factors according to the increasing of the years, and how can the minimum feature size changes according to the reduction in CMOS gate array process. How can it is scaled down by a factor different type of structures. So according to that, I will explain here according to year wise the reduction of minimum feature size, that is called feature, means width length process according to the that is according to the chip area, and the difficult CMOS gate array process which is used in. So that is the first in the table I will shown here the years and each are the minimum feature size, that is in micrometers. So in 1985 that is basically equal to 2.5, and when the year increases it is reduces as the year in process way. So in 1985 feature size is 2.5 micrometer, in 1987 it is 1.7, in 1989 1.2, in 1991 1, and 1993 0.8, 95 0.5, 97 0.35, and 99.25, and at the time of presently the minimum feature size is basically 15 micron here, something according to it. So as the year increases, minimum feature sizes decrease and means dimensionally according scaled by a factor of particular S value. So I will also explain here, that is basically the scaling of the MOSFET when we scale down by a factor of S. Then I will show here the diagram. In this diagram basically gate, source, drain, where we use the different type of widths. I will take here the width is scaled down by a factor of S, same as it is the length between the drain and source, that is reduced, that is LS divided by L is normal way divided by S. When we talk about the doping densities, higher concentration densities of source and drain, that is multiplied by a factor of S, that is denoted by in this diagram ND into S source and ND into S for drain purposes. When we talk about the junction depth, that is reduces by a factor of S. I will show here XZ dash is equal to XZ divided by S. When we talk about the thickness, it is also oxide thickness, that is basically also reduced by a factor of S. TOX dash is equal to TOX divided by S. And we talk about the substrate doping densities, Na dash, that is basically the Na into S. So these are the basically dimension structures by which we have shown how can we reduce the device by the scaling factor of s. Sometimes it reduces in terms of s multiplied by s factor, or it is sometimes in terms of different ways it is divided by a factor of d, that is scaled upon factor of s. So according to that, when we talk the different two ways, that is namely classified as constant field scaling and constant voltage scaling. First I will take here the constant voltage scaling, constant field scaling, that is also called the full scaling. So according to that, when we talk about the full scaling, the scaling option attempts to prevent the preserve the magnitude of the internal electric fields in the MOSFET. So while the dimensions are scaled down by a factor of s, to achieve this goal, all potentials must be scaled down proportionally by the same scaling factor. So when we talk about the threshold voltage, the Poisson equation describing the relationship between the charge density and electric field dictates basically the charge densities must be increased by the factor of s in order to meet the field conditions. So in the particular table I will explain here the different length, width and particular doping densities which before scaling and after scaling, how can we divide the length, width, oxide, junction thickness, different voltages, the different doping densities reduced or is multiplied by a factor of s. I will show in this particular table. First I will take here the channel length. Channel length before scaling, value of L, then scaled down by a factor of S, L by S, that is the new value L dash after scaling. Channel width W, after scaling W dash is equal to W by S. Oxide thickness, gate oxide thickness, TOX, basically TOX dash, TOX divided by S. Junction depth XJ denoted by XJ, XJ dash after scaling XJ by S. Power supply voltage VDD also divided by a factor of S, VDD by S, that is the new value VDD dash. Threshold voltage VT naught before scaling, VT naught dash after scaling divided by S, VT naught by S. And the doping densities basically acceptor and doping densities, acceptor and donor doping density, that is multiplier factor of S. Na dash is equal to S into Na and Nd dash is equal to S into Nd. So these two doping densities are multiplier factor of vector S. Otherwise all the basically length, width, oxide, junction thickness, voltages all are scaled down by a factor of S in constant field scaling. So according to that, when we use the new capacitance value COX dash is equal to EOX by TOX dash, when we put the all values, new values, that is we get the new capacitance value, that is S into COX basically. When we talk about the according to width and length ratio, that is also called the aspect ratio, so will remain unchanged under the scaling in MOSFET case. So consequently, when we talk the transconductance parameter Kn dash will also be scaled down by a factor of S. Since all the terminal voltage are scaled down by a factor of S, as well as the linear voltage, linear mode current drain equation of the scale can be found as ID dash in linear way Kn dash by 2 twice Vgs minus Vt into Vds minus Vds dash. When we put all the values, then I will get ID line divided by S. So the drain current in linear way, it is scaled down by factor of S. Similarly, when we take the saturation mode drain current, that is ID dash, that is Kn dash by Vgs minus Vt dash ka whole square. When we put out the values S into Kn dash and the different voltage value Vgs by S, Vts by S in terms of Vgs dash, Vts dash, then when we find out the final value, that is ID saturation divided by factor of S. So the drain current in linear way, drain current in saturation way, in both way the drain current is divided by S. So next, when we talk about the power relations, so then power dissipation of the MOSFET, that is basically the drain current flows between the drain and source terminals in steady power dissipated by the factor, by scaling factor. So when we calculate before the scaling P is equal to ID into VDS, and after scaling when we put the values of IDS VD dash, that is basically ID dash VDS dash, that is equal to 1 by S square ID into VDS, means power, original power is divided by factor of S square. So this is scale bound factor of S square. So according to that, when we take the tables, according to that, when the oxide capacitance, that is COX, then the new value is Cox dash is equal to S into Cox multiplied by factor of S in the previous value. When we talk about the drain current is ID dash, that is basically ID scaled by factor of S, ID by S. Power dissipation, that is P by S square, and the power density, power by area, then new value is P dash and area dash, that is P by area not affected by the scaling. So these are the ways in the first of constant field scaling. Next one we have take the value of constant voltage scaling. So in constant voltage scaling, all the dimensions of the MOSFET are reduced by a factor of S, as in full scaling. So the power supply voltage and the terminal voltage remains unchanged. The doping densities must be increased by a factor of S square in order to preserve the charge field relations. So according to the table, the constant voltage scaling is the key dimensions, voltage and densities. So in this scaling, the changes in the device's characteristics are significantly different compared to those of the full scaling. So in the value, I will put here the diode capacitance, that is Cox, increased by a factor of S, which means that the transconductance parameter is also increased by a factor of S and the terminal voltage remains unchanged. So in this way, when we calculate the drain current relation in linear way, ID dash, that is Kn by 2 twice Vgs dash minus Vts dash Vds dash minus Vds square. When I put all the values, then I will put here that is overall current, that is multiplied factor of S. So will S into ID in linear way. So here the current is multiplied factor of S. When we calculate the power, the before and after, when we calculate the power, P dash equal ID dash Vds, when we put the all values, then according to that, when we calculate the values, then terminal voltages are unchanged, but the current is changed, that is factor of S. When you put all the values, so means the S into previous value of power factor, that is Vds into ID. So means the power is multiplied by factor of S. So according to these relations, when we calculate always dimensions, the dimensions in terms of width, length, TOX, junction width, that is all are reduced by a factor of X, that is means W dash is equal to W by S, means denoted by this. When we talk about the voltages, that is VDD and VT, basically the drain to source voltage and drain voltage and the terminal voltages, they are basically remains unchanged. These are not affected by the scaling factor. When we talk about the dopant densities, acceptor temperature, donor temperature, then is increased by a factor of S square, rather than in case of previous constant field scaling, there is a multiplied factor of by a factor of S only. But here we will talk about the constant voltage scaling, that is the multiplied factor of S square. So these are the factors which is changed according to the constant voltage scaling. When we talk about the oxide capacitance, that is S is multiplied factor of Cox, that is the previous way in terms of constant field scaling. Drain current ID, where the drain current is divided by factor of S, but here the in constant voltage scaling, drain current is multiplied by factor of S. When we talk about the power dissipation, where P is divided by S square, but here the P is multiplied by the factor of S. When we talk about the power density, power upon area, that is remains sustained constant field scaling, but in the field of constant voltage scaling, that is power dash divided by area, that is S is cube into power by area, that is multiplied factor of S cube. So these are the relations I will explain here according to the reduction in sizes. When we scale down the sizes according to constant field scaling, constant voltage scaling, means originally when we reduce the size, then the different features are multiplied or divided by the factor of S. So these are the way by which we have reduced the dimension size and how the parameters are changes according to it. Thank you.